unmute yourself. So Ralph, whenever you want to start, go ahead.
I can just start now. Yeah, Happy New Year to everybody first, and thank you very much for the kind invitation to give this talk. So this is about entirely about a recent paper we wrote at the end of last year. Title is De Sitter Quantum Breaking, Swampland Conjecture and Determinate Strings. So before I actually start, let me introduce the gang. So this was in collaboration with two of my students at the Max Planck Institute, namely Andriana Macredou, who is a PhD student, and Christian Kneißl, who is a master student. And let me just say that without their tremendous efforts and dedication, we would not now sit here together and to listen to this talk. So they did really nice work. Okay, so let me start with the general picture. Thank you, Erin, again, for delivering it to our community. So the Swampland program, the aim is to characterize the features distinguishing effective actions admitting a consistent UV completion that we call the landscape from those that do not, and these are what we call the swampland. And so also this talk will be about this endeavor. And so as we will see, we are not really doing something spectacular new or developing a new formalism or so. So we are just collecting things from the literature, essentially, that much more clever people than us were already working out, and then maybe combining them to a, I would say, surprising picture that gives maybe a new view on the relation among the various swampland, de Sitter swampland conjectures that were mentioned in the literature so far. So that's the aim of this talk, to explain, so to say, our route through these problems. So let me remind you, so this is entirely about the de Sitter swampland today. So we have the de Sitter swampland conjecture that was, in some sense, can be proven for tree-level flux string compactifications, and that was derived for the first time, and then was proposed by this famous paper here to hold in general in string theory. So this I call the de Sitter swampland conjecture. And let me mention just for simplicity in this talk, I will mostly discuss this first derivative condition, not the second one from the refined swampland conditions, swampland conjecture. We were making comments about that in the paper, but I was not putting them into the talk. And it was shown later by Bedroya and Waffer, or proposed, that this swampland conjecture follows from the transplankton censorship conjecture in a certain limit, namely in the asymptotic field limit, though this TCC is weaker than this de Sitter swampland conjecture. And I think it's still a debate whether TCC is a well-motivated principle. And I also don't want to enter that. For me, I just consider this now as a working assumption, and we discuss the consequences of that. Okay, so this is a strong version, I would say, of the swampland conjecture. And Tom Rodelius, I think he never really called it a conjecture, but so let's call it the no eternal inflation principle that imposes a weaker bound on this first derivative of the potential over V, where on the right-hand side, so if you put V to the other side, you see it's not just a constant, so it's still potential dependent with a certain power that depends on the dimension. I mean, the general rule was actually derived in forthcoming paper by Bedroya, Montera, Waffer, and Valenzuela. So please remind or recall the scaling here. This will be important in the following. And they were also showing that more or less this relation here follows or could be realized by applying TCC, which again is a weaker condition than this condition, to a specific model, if you want, to a sequence of de Sitter bubble decays. So you have a sequence of various decays, and in each decay you satisfy TCC, and they were describing this by a sort of an effective potential. And it turns out that this effective potential then marginally satisfies this bound. So we could say that the TCC could be such, or should give in principle such a weak condition that is only this no inflation bound. But in general, TCC is a non-local condition, so it's not local like here. Okay, so we have these two conditions, and in some sense, our observation in retrospect could be interpreted in the following way. So you have two conditions. So on one side, you have a condition that is still the right-hand side V dependent with this scaling here, and the other one is constant. And you see, if you, from this perspective of the no inflation principle, if you choose n equal 2, you get here a constant. So you would say that this condition here gives you the two-dimensional condition here for each dimension. Yeah. So for n equals 2, this becomes V independent. And if you have read all the string theory literature from the past, you might remind yourself that precisely this behavior is reminiscent of the high temperature phase of string theory. So I will review this in the sequence of the talk later anyway, but give you already the main results. So there it was shown that if you compute the free energy density for a string in n dimensions, so there's first of all a phase transition at the Hagedorn temperature, and for temperature smaller than the Hagedorn temperature, the free energy scales like t to the n, again, depending on the dimension. But by Attic and Witten, they were arguing that for t larger than the Hagedorn temperature, it is supposed to scale always like t squared. So to scale always independent of the dimension. And you see the scaling is such that it would be this scaling in dimension 2. And what we will argue now is that these two pictures in some sense are related. So the one of the high temperature regime, low temperature regime, and the scaling in the various Swampland conjectures. But our initial motivation was different. I mean, this I'm just telling you in retrospect what we found. Yeah, okay, so to argue for that, we will actually employ a third conjecture that is in fact older than the Swampland conjectures we string theorists tend to talk about. And this picture was developed by Dwali and Gomez, and also Dwali, Gomez, and Zell, actually here in Munich. And so what we will do is we will study the string generalization of this, what is called the quantum break time approach. So they were not doing string theory, they were having a certain picture of quantum gravity. And their idea is to view de Sitter not as a vacuum or as a solution, but as a coherent state of gravitons over Minkowski space. And the coherence of this state, which means quantum scattering of gravitons from the current states, they argued leads to a quantum break time. So the state disappears with a certain time scale, and they express this, well, we're estimating this time scale by this expression here. So you have 1 over h, which is also the classical decay time, if you want, the Hubble time, and then the inverse of a coupling constant. Effective coupling constants that in n dimensions scales like for a typical energy scale of the order of h, it scales like h over m Planck to the power n minus 2. The picture is not so, well, I must say, for me, it's also sometimes not so easy to understand, but at least they seem to have an argument for this quantum breaking. So they were saying that from the very beginning, quantum effects, so to say, destroy the de Sitter background. Cannot be a stable background. Anyone can compare this, is there a question?
Yeah, can I ask a quick question? So is this quantum breaking time related? It looks like the expression for the page time, if it was a black hole or something like that?
This actually, probably yes, but I actually don't know, I must say.
Right. So
I think it's the base time. So the base time scales as n Planck squared, then divided by the appropriate factor of h. So it depends on the factor of n, I guess.
Mm-hmm.
Only the factor of n, not n minus 1, you are saying? Okay.
I think so. Of course, I think in 4 dimensions, then the page time for the set would scale like n Planck squared divided by h to the third.
Mm-hmm.
Mm-hmm. Yeah, sorry, I was not asking myself this question so far. They found this, and we will also recover this result later. So for me, this state of gravitons, to compare with something I know from string theory, you know that deep D-branes can be described as coherent states of closed strings in the boundary state approach. So maybe you can think of this as some sort of non-BPS brane that decays eventually. So this is the analog of what they consider what will happen to de Sitter space.
Sorry, Raf, can I ask again? In this picture, do we know what is the endpoint of the decay? Do we know what the de Sitter decay?
No, I don't think so that they know that.
Thanks.
Minkowski space probably. I mean, they have a much simpler picture than string theory usually use. I mean, they just consider this as a bounded of purely gravitons, so they don't have any other fields in the game, just four-dimensional Einstein gravity, and the scheduling is just the de Sitter space is considered as a solution, or not a solution to this, as a bound state yeah, of gravitons over that state. This is not important for our purposes here. I'm just recapitulating this because I will use a different approach.
Ralph, can I comment, Ralph, maybe on that?
Yeah.
Is okay? Hi, this is Ian.
Yeah, that's even better. Thank you.
Hi.
Definitely.
Yeah, I mean, so yeah, first of all, yes, it's absolutely correct. It scales like pages time. But there are two things. So this alpha has to be taken, the strongest alpha in the construction. So for example, if you construct the sitter as a de-Broglie state, then, and you also have, for, let's say, open string coupling, closed string. So whatever is the strongest, that contributes the fastest in the quantum breaking. So in pure gravity, this is the expression, the last one. So in pure gravity, if there is only gravitational interaction, and we ignore the source, if we think of source as dead cosmological constant, then this is the quantum break time. Exactly, it comes out as a pages time in that case. For pure gravity, it literally gives the pages time. And the second point is that actually, we also were motivated by string theory because implicitly, I made it very explicit in my last paper, because the reason why we're forced to consider de Sitter as a coherent state is because in S-matrix theory, there is no other way to consider it. It's simply, in S-matrix theory, we only have vacuum and excited states. And this is just, is imposed upon us by the S-matrix formulation of string theory. So therefore, this is a fully stringy, also fully stringy, fully stringy argument also. So yeah, sorry.
No.
Yeah, but in this case, you're using classical time, right? So it means that classically it could decay faster, right? Or what is the classical time?
Right. So in other words, so this is a general expression for quantum breaking. By the way, this quantum breaking phenomena is very interesting. It's universal. It's exhibited by different systems that are saturated. So the saturated system, such as de Sitter, is also a saturated system. But basically, when occupation number is given by the inverse coupling, so that's the saturation point. So then quantum breaking time is related to the classical evolution time of your system divided by the quantum coupling alpha, and classical evolution time for de Sitter is Hubble. So for de Sitter, you have classical evolution time. T classical and T quantum, it's very important to understand that quantum breaking time is not a decay time. It's true that de Sitter evaporates and decays, but quantum break time is when system fully departs from semi-classical evolution. And for de Sitter, in order to be consistent, before that system has to exit classically that state. So classically, you have to find a graceful exit before system quantum breaks.
I see. So it's like two stage process, right? Classical decay and then the decoherence or whatever this quantum time.
Classical, as I said, it doesn't have to be a decay. It's a classical time evolution. Whenever you have classical time evolution, for example, de Sitter, we have classical time evolution, and then there is a quantum departure, right? Yes. So sorry, Ralph, for.
No, take the time. I don't have the answer to the questions. Okay, good. Maybe I continue.
Oh, sorry. Can I ask one more question?
Yes.
Could someone explain why the semi-classical description should break down at this point? Is there some sort of intuition viewing this as a coherent state of gravitons? Why this time is special, or what it is that goes on here physically?
Yes, so there are several things that go on. So what happens is that de Sitter loses by this time, it loses half of its constituents. So if you start with a coherent state that has a certain occupation number, which is imposed by classical relation between Hubble and the metric, it loses half of those constituents. So essentially becomes that classical source can no longer accomplish the goal. It can no longer populate the state by enough constituents. So this one thing. And second effect is very important, is self-entanglement. So what happens is that when the de Sitter depletes, the remaining state becomes more and more self-entangled. It is also entangled with radiation. From that point of view, it's very similar to entanglement between black hole and radiation. But what is very important is that it also has self-entanglement. So the remaining state becomes more and more entangled, and by this time it becomes maximally entangled. So basically, no trace of semi-classicality anymore. So that's the physical meaning.
Okay, should I continue now?
Yes, please. Sorry.
Yes.
Good. Okay, so there's this quantum breaking time. Yes, okay, so Gia was explaining a little bit about it. And then in addition, there was the proposal that this quantum breaking actually should not occur. So that the theory must censor it by providing, say, a classical mechanism, like a rolling down of a field, that leads to a faster decay of de Sitter. And if you look at this computation and you generalize it to n dimensions, you find that for a slowly rolling field, that this implies precisely the bound we were already seeing from this no internal inflation conjecture or proposal. So there is a coincidence between the two. So the question that we were initially asking is whether one can also get the de Sitter Swampland bound, so the stronger condition as well. So it's pretty clear that here, so the input was more or less that you have gravity in your theory. So maybe you need to add some more string ingredients in the quantum break time picture. Like there are many things, p-forms, KK modes, string excitations, and so on. But how do we then compute the quantum break time? Maybe Gia knows. And maybe there was also this work by Brahma, Dasgupta, and Tata, where they were writing down coherent states in string theory that were also time dependent and making a very similar proposal actually. But what we were taking a different route, and so we were using it, so to say, from a completely different direction. There was this paper by Tomi Makanen in 2017, and they were also finding, or he was also finding sort of an instability in the de Sitter vacuum that is naively from a completely different type, but it leads to the same formula. So maybe you can also view quantum breaking of de Sitter, in this case now, as a result of tracing out states beyond the de Sitter horizon. That was his argument. So he was doing semi-classical computation, looking at the field theory in curved space or on a de Sitter background for the Bunch-Davis vacuum, and then integrating out or tracing out the states beyond the horizon. He was also finding an instability that I will explain in a moment in more detail. And as we will see, this picture that appears here, for that, at least we found a way to generalize this also to string theory or make a proposal for that. And a surprising new aspect appears that is will be related to this Hagedorn temperature and Hagedorn transition. So the objective of our paper was to find this missing link here. So from the trans-Planckian censorship conjecture, we have seen that in the asymptotic moduli space limit, you find the strong version, and by this de Sitter bubble decay, you can at least find a model, so to say, proposal which satisfies only marginally this no internal inflation bound. From the quantum breaking approach, you find the same bound, but what about here? Is there also a relation between the two here? This was our question. And for that, we are using now this approach by Makanen that I will present. Of course, I cannot present all the details. That's all in the paper. And we added a little bit to this new picture also. This is, I think, the bulk of the paper actually that we wrote. But for us, the main message is what I will explain now in a few pages here. So the idea is to write the Bunch-Davis vacuum of a scalar field in de Sitter as an entangled state in the product Hilbert space of states localized inside and outside the horizon. And then, being an observer, so to say, in the center of our de Sitter space, we trace out the region outside the de Sitter horizon. So this will be, so to say, the quantum thing that we are doing. Yeah? So we are computing a reduced density matrix and then compute expectation values with this reduced density matrix. So let me review a bit and also maybe add our generalizations. So you consider a scalar field on a de Sitter background with a Friedman-Robertson-Walker line element. This is in one patch, and which has a horizon that is given by the inverse Hubble scale. But of course, this horizon is not very explicit here, but it's best visible in the so-called static patch, which is time independent, but has these two regions where it's valid, so to say. So in region A, this is inside the horizon. And you can also use this formula outside the horizon, but then of course you're exchanging time and space here. Okay, so these are the two regions. And the aim now is, yeah, we know what the Bunch-Davis vacuum is in, so to say, in this patch. And the aim, or the problem that he solved, is to write it as an entangled state in this product Hilbert space, and using then this patch. Now this is appropriate to talk about states localized inside and outside the horizon. So this is all very explicit. So one considers an action of a scalar field. De Sitter background is the background. And so what Markkanen did, he was using the conformal case, because then the answer is the most easy one, so to say, the most clear one. So he was setting the mass of the scalar to 0 and introducing this conformal coupling here to the Ricci scalar here. If you have a certain value here, then this theory is conformal, and that's the theory that he was considering. So what we did, and how we generalized it, is to look first of all also at the massive case, because in string theory we have also massive excitations. And in string theory, it's not so clear where this coupling should be come from. So we were setting this parameter to 0. So then you can solve this equation and find the following mode expansion. I'm just showing this to show you that this can be explicitly be done. It's not so important what is written here, but it's just to show you that this can be done explicitly. And it's analytic, so you get here this hypergeometric function in the solution. You get spherical harmonics in higher dimensions. Here you get the modes and so on. So this is explicit. And you can construct a similar solution outside the horizon. And then what he did is to argue that one can also find two continuous linear combinations of inside and outside that are continuous above if you cross the horizon. And there you see for the first time the appearance of this thermal factor, gamma here. So e to the pi I k is momentum over h. If you identify h the usual way of the Gibbons-Hawking temperature, and then you see that this is a thermal factor. The Bunch-Davis vacuum, the condition for that can be translated into a condition on the modes in our solution, relating the modes inside and outside. So this looks a bit like gluing conditions for boundary states in string theory even. So the solution is also very similar. You find, for the properly normalized solution, you find that you can write indeed, this was the aim, the Bunch-Davis vacuum, as a sum over states localized inside and outside the horizon. So that is what he did. And this is what he called coarse graining. Coarse graining comes by tracing out now the unobservable sector in the region V, so outside the horizon. And we have achieved the goal that we have written the Bunch-Davis vacuum as a linear combination of entangled states. And the resulting density matrix can be explicitly written down. It has the form of a thermal state of temperature h over 2 pi, the Gibbons-Hawking temperature. So here you see that in the Bunch-Davis vacuum indeed is a thermal state. So that's nice and explicit. Next thing one does is to compute the coarse-grained energy momentum tensor. So you take the vacuum expectation value of the various components of the energy momentum tensor, say of the energy density and momentum. And since we are interested in what observers at the center of their static patch see, so in the middle of our patch, he worked at leading order in h over r. And what you can show then is that we have explicitly shown that in the two regimes at least, so the mass much larger than the Hubble scale, the mass much lower than the Hubble scale, that you can get a contribution to this to these values of energy density and pressure that have a nice interpretation, because they are nothing else than the flat space contribution of a thermal energy density of a state of mass m. Yeah, so with this, here's the Boltzmann factor, here's the energy per state, and here you integrate over the momentum, so to say. But you see, this is a flat measure. So what you have done, there is a contribution. I'm not saying that this is the complete answer. I'm just saying that there is a contribution to the energy density that has this nice flat space thermal energy contribution. There are corrections. The corrections only vanish in the case that Markkanen himself was considering, in the conformal case. In general, there are curvature-dependent corrections. Curvature is h here. So there are h-dependent corrections, but one can show that if you carry out this integral and you express everything then in terms of h, the scaling with h doesn't change. So the scaling with h is the same for the flat space contribution as for the corrections. And as long as we are only interested in the scaling with h, it's sufficient, so to say, to consider this flat space contribution. We don't have to deal with curvature corrections. Oops, sorry. Yeah, and the reason why I'm emphasizing this is because this picture, of course, can be generalized to string theory. Of course, in string theory, we don't know really how to quantize this on a de Sitter background, but we can compute the flat space contribution of an ensemble of strings in a temperature T.
Ralph, sorry, can I ask, just to see if I understand, the expressions you wrote there for the energy density and pressure are supposed to be valid in a small region near the center of the static patch, is that right?
That's correct, that's correct. There are corrections, R-dependent corrections, but you see, we are the observer, we are sitting in our patch, we see the horizon outside, so this is the thing, how we in the center would describe what, yeah?
Yeah, this is what a thermometer would say.
Yeah. Yeah, this is I mentioned already. So there are H-dependent curvature corrections. And it's also very important. So I was writing down two components of the energy momentum tensor here. It's not so easy to compute the other ones, in fact, and in particular at the horizon. Markkanen did this in two dimensions, and then he was realizing that, of course, there is an inflow. There's an inflow, and there must be an inflow of energy also from the horizon, because the energy density and the pressure that we were computing before is time independent. So you have an expanding de Sitter space, and you have found that there's a matter contribution now that is time independent. So you usually would expect that they get diluted and redshifted, but that's apparently not the case. So there must be an inflow of energy from the horizon. Well, that's the picture.
Can I maybe ask a question about that?
Yes, please.
So I think so. When you're saying that there's a net inflow of energy, I think that means that if you express the stress tensor in static coordinates, that there is an off-diagonal term.
Absolutely, yeah. There's a 0, I component, indeed.
Yeah. So then I'm worried that I think the only way. So what happens if you have this off-diagonal component? Then I think if your stress tensor is conserved, yes, then you can have an off-diagonal component, and automatically that means that there's a singularity of the stress tensor either at the future or past horizon.
Yes, okay. That's true. I think that is also what he found, if I remember it correctly. So we have this explicit expression only from the Markkanen paper in 2 dimensions.
Mm-hmm.
Once we find it.
So but I'm a bit more general. I think my confusion is a bit because I think because you're starting in the Bunch-Davy state and you're writing down a density matrix. So that, and if you could compute the stress tensor in the Bunch-Davy state, you will get an answer that is respects all of the de Sitter isometries.
Yes.
But now you're saying that if you do this coarse grading, you have a reduced density matrix. And if you compute the stress tensor, then somehow the de Sitter isometries are broken. So this confuses me because I think the stress tensor it's a local operator. So I don't see how the symmetries could change by doing a tracing operation.
I think I don't have a good answer to your question. So what I remember is that he was writing down the off-diagonal components explicitly in 2 dimensions. This is more or less exactly solved with this model. I think he has an explicit expression.
Yeah, I agree. Yeah.
R times R. And I think it was like 1 over 1 minus H times R. So indeed, there is a singularity at the horizon. But I never had these doubts that you have about this result.
At the moment that you have, so this is clearly if you have an off-diagonal component to the stress tensor, that does not respect the de Sitter isometries.
Yeah.
So somehow, if you have this off-diagonal component, somehow you've broken this isometries. But then I guess what I don't see is how just by performing this tracing operation, you can break the isometries.
Yeah, I understand. Yeah, I don't know. I also don't have, I don't have any opinion on that, I think.
Okay, yeah, thanks.
Of course, if the paper by Makan is wrong, or if there's anything that is not consistent, I mean, we're sitting in the same boat. So
yeah, so I do have some doubts about the Marcano paper.
Yeah, so me as a string theorist, so I was learning that, yeah, from that paper, so to say. I don't have really an independent opinion this way.
Okay, thanks.
So we were using his result, and we stay in fall with this result. That's clear. Okay, so let me just summarize what we saw. By tracing out the states beyond the horizon, an observer in the center of their static patch thermal energy density and pressure with an equation of state parameter. This I haven't argued, but we have looked at many examples, omega larger than -1. And importantly for us, whose scaling with R, H is already determined from the flat space contribution. So what he was then doing, so he was seeing that if you now take this back reaction of this extra matter component, OM here, into account into the Friedmann equations, but you can do this, but you also have to satisfy, in order to satisfy the continuity equation, if you make this ansatz, you find that you also need a little change in here, and that is here time dependent. So this is describing this incoming flux. This component that still looks like a cosmological, scales like a cosmological constant with omega -1. So this is his description of this system, so to say, that the observer in the center of the static patch, how he would describe now this universe. Yeah? So he finds extra matter, but it should not be diluted. So, and he can compensate for that by introducing this inflow of energy here, which is time dependent. Then you can show that the continuity equation is indeed satisfied. It's also in our paper. But if you add the two equations, these two here, you see, of course, the first term here cancels out, that in that case, H dot is not equal to 0. So the Hubble parameter has to change. And if you use now the scaling of rho in n dimensions, so just the field theoretic scaling of the energy density of a gas of particles at temperature T, which is H here, scales like H to the N. And then if you use this, you can integrate and you find that the Hubble parameter is changing with time. And it leads to a decay, so that leads to, so H gets reduced and the typical lifetime, as you can read off from here, scales like M Planck n-2 H over n-2. And that's the same expression as have been found by Duali Gomez-Cell for their quantum break time. Of course, this is a completely different approach. And I also don't know how these are related, but as a matter of fact, if this computation is correct, they give the same answer of a quantum instability of the zeta space. And we believe that this is not just an accident, that this is another description, say to say, of the same physical process. It's still quasi-classical, but you did this additional step of integrating all these things to define reduced density metrics. That's the quantum thing that goes in here. Okay, so if this is such...
sorry, may I ask about this?
Yeah, please. Why?
I'm confused about... I was always thinking that if I'm inside my Hubble patch, in the sitter, then I should not look at the quantum superposition of all these large distance or large scale modes. Instead, I really should look at the decohered classical value, which I observe, because by my observation, I fix the value of phi by me being there. And so I have doubts about the correctness of using the full quantum superposition of all those fields from outside. Maybe you know the work of Starobinsky, where you think of classical value simply jumping around stochastically. And I always thought that this is the more correct approach to treat the effect of long distance modes on you as an observer inside your patch. I wonder whether you have an argument against that perspective, that observer perspective, which fixes the value.
For that, I think I'm really not the right person probably to ask. No, I don't have that. We were just taking this as it is, the Markan paper, and then We take it for granted.
You see, you locally measure lambda, so you also measure the field value. So you are not quite seeing this whole quantumness that you are using. That's my worry.
Mm.
Okay, good, thank you.
I mean, there are doubts everywhere in this. So let me just continue maybe making the argument.
Sure.
And you will see, I mean, there are nice coincidences, put at least this way. One coincidence is that if you proceed like what I did, what Makan did, you find that the quantum breaking time, or this time scale that he found here from the change of age, is the same thing that Gia and friends found in their quantum breaking time approach. Okay, so, but this computation, so to say, at least we have an idea of how this might look like in string theory. And so there's a natural generalization here, even though you cannot follow every step, of course, but you have this terminal meta contribution, which is flat space. And of course, we have also something like a free energy expression for strings moving at finite strings in a temperature above of finite temperature. And we are using then the same expression for that in string theory. So assume one has constructed an n-dimensional tree-level string model that features modalized stabilization in a tachyon-free de Sitter, or at least quasi-de Sitter phase. So tracing over the unobservable states in the string Hilbert spaces, I think, to my knowledge, is not a yet solved problem. So we will assume that this procedure again leads to an extra quantum contribution to the energy density in the observable universe, that is described by the string theoretic flat space thermal energy, some thermal energy momentum tensor. That's our assumption. Oops. Okay, to proceed, let me just recollect some facts you might know about strings at finite temperature. What you are using here is that the free energy of a gas of particles at temperature n in n-1 spatial dimensions, that this is equal to the n-dimensional vacuum energy of a string compactified on a Wick-rotated time direction with radius r, 1/2 pi t. That's the usual description, also used in field theory, but this can be generalized to string theory for each mode. And then people have already written down an expression, in the past they've written down an expression for the free energy of a string at temperature t moving in uncompactified flat dimensions in string frame. And this is this expression. So it looks like a generalization of the string partition function where you compactify your string on a certain rate, on a circle of radius r, and do a certain orbifold. I come to that. Yeah. Sorry. Okay, in addition, so the string partition function is over the remaining string mode. So the continuous momenta is already carried out. This explains this exponent here. And so the remaining partition functions contains the string oscillator modes, internal KK, and winding modes. And in addition, this what's called Matsubara momentum and winding modes for the thermal cycle compactification, where it should be such that bosons couple always to integer and fermions to half integer Matsubara modes. And this can be easily described by string constructions. So the way I was using it is that this theory at finite t is closely related to a winding Scherk-Schwarz orbifold. And this is a compactification of string theory on S1 times -1 to the space-time fermion number times a winding shift orbifold. And this acts on a KK and winding mode with a factor -1 to the m. So a usual shift is acting by -1 to the m. This is n. This is why this is called a winding shift. Okay, so this can be made very explicit. We know how the partition function can be computed. Of course, we get twisted sectors. And then there is a certain map between the characters of this orbifold and the final terminal partition function. So you exchange two of them. So let me just keep that short. So eventually one gets the terminal partition function in string theory for superstring theory. And that's a certain combination of the bosons in your initial theory times a certain contribution from the KK and winding modes for the circle compactification. So this indicates that here we sum m over all integers and n winding modes over all even integers, and here odd ones and so on. And you get new sector, a twisted sector here. And yeah, it depends, of course, on the model in question, what this partition function explicitly is. And just to give you an example, so for type 2b, for instance, the 10-dimensional type 2b partition function can be expressed in this hopefully familiar way. You have the GSO projection left and right independently, and you write everything, the fermionic contribution, in terms of SO8 representations here. So if you do the math, so this leads to the terminal partition function of this form here. So you have certain combinations of these characters multiplied with these KK and winding contributions. And I think the most important thing is that here, what is indicated in blue, there is a new tachyon potentially appearing here. So new sectors appear in the twisted sector. And here there's the potential that this is tachyonic. And indeed, this combination turns out to be tachyonic, the lowest lying mode, for temperatures larger than the Hagedorn temperature. So at the Hagedorn temperature, a certain mode is massless and becoming tachyonic beyond that temperature. And this was the reason why this temperature is not thought to be these days as a maximal temperature, but rather as indicating a phase transition to a new phase. And yeah, so this Hagedorn temperature indicates a phase transition where the binding mode gets a non-zero expectation value. And there's a famous paper, of course, by Attig and Witten, even from 1988, and they argued that this is a first order phase transition indeed, and at which even a tree level contribution to the free energy is generated before everything was one loop and higher. And moreover, it's being now at a tree level, so you expect it to strongly back react on the geometry in question. So this is, they always argue that this might be analogous to the deconfining phase transition in QCD. So this phase transition is expected to be dramatic, and completely new degrees of freedom will be probably revealed at temperatures higher than Hagedorn. As far as we know, there's no consensus yet what these new degrees of freedom of string theory are at high temperature and by which theory they are described. It might be, I mean, there are various things have been discussed in the literature and some things you might expect. So, I mean, a closed string tachyon condensates. So you think that the center charge should decrease. So you might think that some subcritical string theory comes in here. Or some people also considered lattice theories. Or if I understand this recent paper by Agrawal, Bukov, Ovid, and Kumrum correctly, they might have something in mind that there's a topological theory at high temperatures or high energies at the beginning of the universe being relevant. And for me, this should be the same thing as this high energy phase high temperature phase, excuse me, of string theory. So we don't know what it is, but.
Sorry, Ralph, stupid question. How do I have to imagine physically realizing such a high temperature phase? I mean, to avoid it creating a black hole, creating horizons.
It could be that in this high energy phase that precisely black holes are your fundamental modes. Right, so it's not, even if you get black holes, okay, then in this high temperature phase, I would say then your modes, black holes will be part of the game.
I mean, I'm afraid that if I create a plasma like that somewhere, it will just close off due to the horizon and it has no meaning to discuss the local dynamics of that phase. That's my worry. I'm very naively.
I think the theory was also mentioned by Attig and Witten in the initial paper, but there are many papers after that, and people were trying to reveal, so to say, what's going on here. They also studied the phase transition in more detail, so that you're working very close to the Hagedorn temperature. So I think for me, it's just in the moment a black box, and there were also indications that at high energies, people like David Gross were looking at high energy scattering amplitudes. And there were also a great simplification occurring at high energy scattering amplitudes, for instance. So that at high temperature, high energy, new degrees of freedom of string theory, or that the description of string theory becomes much simpler at high energies and high temperature.
Maybe I have to think of a limit when the string tension is much below in Planck, right? I see. Maybe that's a limit to think of, right? I have to go to a 40 world with very low string tension, such that I don't get 40 back reaction. Sorry, maybe that's the answer. Yeah, I apologize. I think it was a stupid question. Okay.
No, it's not, definitely not a stupid question.
Yeah.
I think it's not.
No, just to make sure that I have a proper 4D world with such high temperatures is non-trivial, but I think by lowering the string tension, you can do that. Okay, thanks.
Okay. Okay.
Alpha, I also have a question. Can we relate this Hagedorn transition with an infinite tower of states that is becoming light when we go to the asymptotic regions of the space? I mean, like the way to resolve this infinite tower of states is to go to this phase.
So my immediate answer would be we are not seeing this as some infinite distance limit or so, right? So the Hagedorn temperature is related to a certain radius of a circular compactification that is not at infinite distance in the moduli space of these circles. It just happens to be at a certain radius, a tachyon appears. So I haven't thought about it, but I would think that much more dramatic things are happening at the Hagedorn transition than just infinite tower of states becoming light.
Okay.
Also string excitations or KK modes. Okay, I continue. So Artik Witten argued in the old famous paper that actually the extrapolation of the one loop free energy to this high temperature regime still gives a reasonable result. And what they found is indeed a quadratic behavior. Yeah, where the prefactor in the type 2b string was related then to the one loop type 0b partition function, vacuum energy. Yeah. And so this was independent of the dimension. So it's precisely the behavior that I was mentioning in the beginning. So they already found that the one loop amplitude shows this quadratic behavior in every dimension. The point is that here the winding Matsubara modes become the most relevant contribution, and they create this t-square behavior. And this is generic and could also be seen, by the way, as a consequence of this what's called thermal t-duality. And just formally, we have this expression for the partition function, and it turns out that the thermal partition function, roughly speaking, at the inverse temperature is the same as the winding Chirac-Schwarz partition function at the temperature T. And if you now use the formula for the free energy, then this behavior immediately follows. By knowing that in the type 2b string, letting this radius of the circle compactification go to infinity, it becomes the type 0b partition function. Okay, so it seems to be, and this was also recapitulated in a series of papers by Kaleb, for instance, that quantum gravity at high energies, high temperatures behaves rather as a two-dimensional field theory. And it's quite intriguingly, the same observation was made in other approaches to quantum gravity, like causal dynamical triangulation or asymptotic safety program. And Kaleb wrote a series of papers where he was reviewing all these different approaches, and they all come down to this two-dimensional behavior. So maybe something is happening here. And
can I ask a nice question? And this 2D and like theory has anything to do with this 2D and string theory?
Question. Maybe yes. Needs to be worked out in detail. There were proposals. Yes, it could be a two-dimensional string theory.
Okay, thanks.
Yeah, that the condensation of the tachyon changes the 10-dimensional string theory to a two-dimensional string theory. But it could also be, but this would not be immediately a topological field theory. Well, it's topological, gravity sector is topological, but it's, first of all, it's a string theory. Of course, then for sure you get this quadratic behavior. That would be guaranteed. But still, I think it's not clear. And then the question is, which one? Which two-dimensional string theory? So I think this question is not, I mean, maybe I'm not, I simply don't know it, but I think this question is not settled, what the condensation really leads to. Okay, for us, the most important thing is we are assuming that this temperature scaling is correct, like T square. So let's discuss these two phases, and I call them, according to this paper by Kumrum, the low temperature regime I will call now phase 2, and the high temperature regime I will call phase 1. So how am I doing with time, by the way? Okay, I'm already overdue. Can I still continue? We had many questions already.
Yeah, you can go on.
Okay. Okay, so in the low temperature regime, the winding modes, the winding Matsubara modes are very massive. So they give a highly suppressed contribution to the free energy. And in the limit T goes to 0, it's known that precisely the free energy just gives you the one loop vacuum energy. And in 4D, for instance, we were plotting just the main contributions to the free energy. And indeed, the free energy scales precisely what you would expect from a field theory, for field theory. So the energy density, like in 4 dimensions, really scales like in a quartic way, which is evident here when you compute the fourth root of this result, which gives you really a straight line. Moreover, one can numerically check also that the equation of state is like for free gas. So string theory reproduces the field theory result. And so also when we now do quantum breaking, so we use now this free energy or the corresponding energy density as the result of the, so to say, flat space contribution to the energy density also for the theory when we integrate out the states beyond the horizon in the de Sitter space. Yeah, so we take this expression and say, okay, but this must be the one. If I could do the Markkanen computation for a string theory, I should see this contribution, this flat space contribution, and this is how, from the general expression string theory, we know how it will behave. There are extra stuff probably, but we also believe that it scales in the same way with H, and we only need the scaling with H to make an argument for the computation of the quantum break time. Okay, so we get the same as in field theory, but there's a couple of small issues, I would say. So first of all, in string theory, the Planck scale is derived quantity, so fundamental quantity is MS actually, and it's the relation. Moreover, we have to be a bit more careful. We were also using in this estimate Einstein's equation, yeah, and this gets corrections in string theory. So string theory generates higher derivative corrections, scaling like H over MS. Corrections to the Friedmann equations, but at low temperature, so low H, I mean, this is controlled, so we are in a controlled regime, so we are fine. Moreover, if we have a larger volume, say not string scale volume, and working still in effective n-dimensional theory, this is more massless K states, so to say, this tower of K states becoming light. The scaling, you will find indeed from the free energy, you find an additional factor of this overall volume, internal volume in the scaling. And then the quantum break time gets modified that instead of the Planck scale here, you will see the string scale. Yeah. And so this will also change the inequality. So to avoid quantum breaking, that the classical potential has to satisfy this bound. So the only change is that GS now appears. So this shows you that it's a one loop effect here. And that instead of Planck scale, you find here the string scale. It's sort of the species scale. We had an argument in the paper that naturally here again, the species scale appears for this light tower of KK modes if E is substantially larger than 1. Okay, so that's the low temperature result. No, nothing new. But for the high T phase, phase 1, we see the difference. So here it's the winding modes that make the dominant contribution to the free energy. And when you do the integral, you find that in all dimensions, it scales quadratically, as Attic and Witten are saying. So again, straight lines in all dimensions. Here's the square root. So in all dimensions, we find indeed, or we could confirm the quadratic scaling. So what does this mean? Okay, so here it's a bit harder now, because if you now want to argue for to compute the quantum time, and we're using again Friedmann equations, but here they are correct from the low energy point of view, low temperature phase point of view. Of course, we are expecting corrections here. We are now in the regime where the curvature corrections become relevant. But moreover, we know that there is a phase transition in between. Yeah, so of course we would like to do the computation directly in phase 1, the high T phase, but we don't know what the theory is. But we believe on this quadratic scaling. So the one loop terminal partition function this is exact, at least the expression that we wrote down, but we know this winding tachyon, so there is a phase transition for sure, but we believe or follow Witten and that this scaling is generic. So we make now two assumptions. We assume that in this phase, even though it's largely unknown, the following two aspects hold. First of all, let me mention this first. So we have this quadratic scaling, and at leading order, in this new phase, if you would describe it generally in this new phase, the equation of motion is still given by Einstein's equation. That means in this regime, there exists also a controlled gravity theory. This is an assumption. Otherwise, we cannot use Friedmann equations. So as an example, maybe say it's a topological theory. Maybe it's a three-dimensional topological theory, like gravity in ADS. Then you would still get Einstein's equation at the lowest mode, the lowest order. And so you could still compute the quantum break time using the formulas I was showing you before. So something like this we have in mind here. For 2 dimensions, I wouldn't know how to compute it correctly, for instance, because then the Einstein tensor is vanishing. And gravity is purely topological. Good. So if we now use that and do these two assumptions and use the same formulas as before, so the quantum, it's clear because we have the 2-dimensional scaling everywhere for every dimension, that the quantum breaking time in phase 1 in n dimensions is the same as in phase 2 in 2 dimensions. So we know what the expression is. So we get really the constraint from the de Sitter conjecture. Here it scales again with the string coupling because we have assumed a one loop. We got the information from a one loop computation. And so it's not a pure C number as in the de Sitter conjecture, but taking again the Artig-Witten argument into account that there might be a zero loop contribution in the phase transition. So this factor of GS could just be an artifact of the extrapolation of the one loop terminal partition function to phase 1. So if you do a genuine computation, you might find that this is gone here. So recall that Artig-Witten argued that in phase 1 there will be a tree-level contribution. A lot of assumptions. So it's important, of course, to check this by genuine computation in phase 1. The caveat is we don't know what the physics of this phase is. But we could take it, so to say, as a guideline to get for sure these two, to make this picture, so to say, that we propose consistent, we have then two things that we want to have in that phase. Sorry?
Yeah, sorry. Can I ask to see if I understood? So the picture here, we're in a de Sitter now, which has a Hubble scale comparable to the string scale, and therefore it's in phase 1, right? Or why are we looking at phase 1?
Yeah, yes, that's true. That's true. I mean, the Hubble scale is, so the temperature is larger than the string scale, indeed.
All right, okay. And in that regime, we recovered the de Sitter conjecture.
Yeah. So in a regime that you usually not consider at all. Yeah.
Thanks.
Not in coupled string theory. But here I have a picture that explains what you were asking. Of course, you can now also ask, so what about the asymptotic field limit in phase 2? This is the one where we found from the TCC also this de Sitter Swampland conjecture. And you could maybe ask, so first of all, you have now these two phases here. And so there's a phase transition in between where H or temperature is of the order m. So to the left, we have this bound here that was given like by the usual bound from the quantum break time, for instance, or the no eternal inflation conjecture. And on the right-hand side in phase 1, we have the constraint from the de Sitter Swampland conjecture, so the strong constraint in every dimension the same. So how do I see? You see, it's strange now because we usually think that also here in some asymptotic limit, we would expect to see this condition. Yeah, how could this come about? Of course, we are not sure, but at least we have one argument, and this employs the emergent string conjecture by Lercher and Weigand, meaning that an infinite distance limit is either a decompactification limit or a tensionless string limit. So this means that going to some asymptotic field space, the string scale goes to 0, either of the full theory or of this tensionless or of this extra string here. And so this goes to 0. So this means that the Hagedorn transition, so to say, is moved to the left. And in the very limit, so to say, phase 2 disappears completely. So you see much more, so to say, of phase 1 already at very low values of H. This is just a possibility. At least we could see that in this limit, phase 1 dominates the whole region here. Phase 2 disappears. I'm almost done. I'm getting tired already. Unfortunately, it's quite late here. So, so we did. What have we done? I mean, of course, I'm not making too many claims, maybe, but at least we developed a line of arguments that we think mutually support the various assumptions made. So first of all, and this is, of course, everything falls with that quantum breaking due to tracing out, that quantum breaking can be described by tracing out states beyond the horizon. Good. Moreover, we find that we assume that the scaling with H is determined already by the flat space thermal contribution. And that this we could easily generalize to string theory. And we were assuming the universal 2D behavior in the high temperature phase. And also that we still have a gravity theory. And so this could provide the missing link in our initial picture here. Remember, this is where we were looking after. So we had quite a tour to various aspects, I would say, in combining these. But at least we see a coherent picture, I think. And we are not claiming that all steps are bulletproof and beyond doubt, but we think that we have at least uncovered potentially intricate relationships among the very basic issues in string quantum gravity. So for the future, I mean, of course, the most pressing question is what is the nature of phase 1? But that's a question that is with us for many, many years already. So that's definitely a hard question. And moreover, this is also another question is, so if we really live in perturbative string compactifications, the actual bound is only this weaker bound here from the no eternal inflation conjecture. Of course, we have this proposal by Irina in France, but maybe it would be nice to see a concrete string theory model that only satisfies the weaker constraint and not also the much stronger constraint. Yeah. So I haven't seen any model yet up to your proposal by this cascade of decays, but really to a genuine, I mean, really a genuine string theory model that satisfies this. Yeah, thank you very much for listening. I'm done.
Thank you, very nice for the talk, Ralph. So are there more questions?